Good afternoon, everyone, and thank you for being here. Today, I would like to share some thoughts on a topic that connects cost efficiency, system flexibility, and the performance of heterogeneous software architectures that combine Linux and RTOS. I will walk you through the key challenges we have faced, the design strategies we have adopted, and how this hybrid approach can provide meaningful advantages even on low-cost RISC-V platforms.
Modern multi-core applications are placing growing demands on processing diversity. To meet these needs, we're seeing more heterogeneous multi-core systems architectures that combine general-purpose CPUs, like the ARM Cortex-A53 and Cortex-R5 found in the AMD Zynq UltraScale Plus, with specialized cores such as DSPs, lightweight CPUs, or soft IP blocks. These specialized cores aren't meant to replace the main processors. Instead, they're there to offload specific compute-heavy tasks when needed. This targeted offloading is essential for boosting overall system performance. In asymmetric multiprocessing, or AMP systems, it's common for the master processor to bring up additional software or firmware contexts on remote cores as needed. This is typically done in a demand-driven way during runtime, with interprocessor communication, or IPC, used to offload and coordinate work. Let's define a few key terms. Master. This is the CPU or software that boots first. It's responsible for managing other CPUs and their associated software contexts. Remote. A remote refers to any CPU or software context that's brought up and controlled by the master. Communication. IPC is what enables coordination between the master and remote, making workload distribution possible. This architecture offers significant flexibility for real-time and mixed criticality systems, and OpenAMP provides a solid open-source solution for such purpose. AMP programming comes with its own set of challenges. These include interprocessor synchronization and communication, isolating and protecting shared resources, managing cache coherency, and ensuring efficient power usage. These are exactly the kinds of problems that OpenAMP is designed to address. When implementing AMP on a heterogeneous SoC, like the AMD Zynq UltraScale Plus, the interface between the application processing unit, APU, and the real-time processing unit, RPU, is often highly device-specific. Heterogeneous SoCs aren't a new concept, but what's changing is the level of control developers now have over them. In the Linux ecosystem, this control is made possible through the remote proc and RPMSG frameworks. The lifecycle management in OpenAMP is handled by remote proc. OpenAMP follows a master remote, or slave model, where the master processor is responsible for managing the remote processor's lifecycle, loading its firmware, powering it up, and setting up the communication channel. Once that's in place, interprocessor communication is handled by the RPMSG component of OpenAMP. RPMSG defines the structure of messages exchanged between the master and the remote, as well as the notification sequence used to trigger communication events. Together, remote proc and RPMSG make it possible to orchestrate complex AMP systems in a portable and maintainable way. On the left, the main processor runs Linux. Within the kernel, the remote processor works alongside generic or platform-specific drivers. Remote processor handles the remote processor's firmware loading and configures fixed hardware resources such as clocks, power domains, I/O pins, and other peripherals during system initialization. On the right, the coprocessor runs a statically linked application and device driver for certain peripheral. Once everything is set up, there's no further dynamic coordination between the processors. The resource configuration is locked in from the start. To go beyond static setup, we can enable dynamic reconfiguration of system resources at runtime using RPMSG and OpenAMP. The main processor still relies on remote processor to boot the coprocessor and perform the initial resource setup. But now, an IPC channel, established via RPMSG or VirtIO, allows the Linux master to communicate with the remote processor through OpenAMP. In this model, remote proc continues to handle system initialization, but resource management is extended through IPC, leveraging RPMSG and OpenAMP to support dynamic, service-based coordination at runtime. The OpenAMP framework was introduced to extend the original Linux AMP architecture into non-Linux environments. It provides a standalone C library that implements both remote processor and RPMSG functionality, making it usable with RTOS or bare metal systems. The design ensures API-level compatibility and functional symmetry with the Linux implementation, enabling consistent behavior and integration across heterogeneous systems. Let's take a look at how flexible OpenAMP really is. In this setup, an RTOS running on the Cortex-R5 cores equipped with OpenAMP acts as the master, while Linux running on the Cortex-A5 cores takes on the role of the remote. The RTOS OpenAMP stack handles both remote processor and RPMSG functionality, effectively managing the Linux environment and reversing the traditional master-slave roles. What makes this possible is OpenAMP's platform-independent, standalone design, which mirrors the remote processor and RPMSG capabilities originally built into Linux, now available in embedded environments. This configuration is especially useful when a lightweight RTOS needs to take control of a more complex Linux subsystem, offering a clean, interoperable solution for heterogeneous systems. RPMSG provides the foundation for interprocessor communication in M systems, enabling the master to exchange messages with remote processors through dedicated communication channels. Each RPMSG instance forms a structured, bidirectional channel between the master and a specific remote processor, ensuring efficient coordination across cores. To operate, RPMSG depends on just two key hardware features. First, shared memory, used as a transport buffer for message data, accessible by both the master and remote processors. Second, intercore interrupts, used to notify the other side when a new message is ready or an action is needed. This minimal hardware footprint makes RPMSG highly portable and well-suited for tightly coupled systems. It enables reliable, low-overhead communication with deterministic behavior, crucial for real-time and embedded applications built on asymmetric multiprocessing. RPMSG doesn't move data on its own. Instead, it relies on ViRT-IO, specifically a simplified version of the ViRT-IO transport model, to handle the low-level data movement over shared memory. ViRT-IO provides the transport abstraction, while RPMSG defines the messaging semantics, such as communication channels and logical endpoints. Together, they form a layered stack for structured and efficient interprocessor communication. In the RPMSA application layer, applications use the RPMSA API to send and receive messages between cores. In the RPMSA protocol layer, it manages message headers, routing, endpoints, and channel setup. In the ViRT-IO transport layer, it bridges RPMSG with hardware, managing shared memory regions, ring buffers as known as ViRT-IO queues, and buffer allocation and synchronization. Finally, in the physical layer, shared memory is used to exchange data buffers, while intercore interrupts, or mailboxes, is used for notification and signaling. RPMSG defines what to send, ViRT-IO handles how to send it. Together, they enable reliable, low latency, and structured messaging across heterogeneous core-subtracting hardware details while maintaining deterministic behavior, ideal for M systems. So far, we've explored the key components that OpenM provides. Now, let's take the next step by looking at some real-world use cases and seeing how these systems are actually put together. In safety-critical systems, the top priority is isolation keeping different software components securely separated from one another. This isolation is essential across all parts of the system: processing units, memory regions, peripherals, and core system functions. The OpenAMP framework supports the development of fault-tolerant systems by providing the communication and lifecycle management needed to coordinate across domains. For example, OpenAMP can enable an RTOS running on a safety-certified core to manage the lifecycle of a non-critical operating system running on an application processor. In case of a failure, the RTOS can simply reboot the non-critical domain without disrupting the rest of the system. Let's consider a patient monitoring system as a use case. Imagine a platform that integrates a cluster of ARM Cortex-R5 cores referred to as RPU and ARM Cortex-A53 cores known as APU. The RPU, running functional, safety-certified software, is responsible for collecting patient vital signs from sensors and monitoring them in real time. The APU runs a high-level OS that displays the data on an LCD and offers network connectivity, but it's not safety-critical. OpenAMP provides the IPC layer that allows the RPU to transmit patient vitals to the APU using RPMSG, while maintaining strict isolation between the critical and non-critical domains. Ultimately, OpenAMP offers a robust and cost-effective foundation for implementing mixed criticality systems, where safety, flexibility, and modularity are equally important. Next, we'll demonstrate how to build an intercore communication system using OpenAMP on a low-cost RISC-V platform with a heterogeneous multi-core architecture. The system will run both Linux and ThreadX, two open-source operating systems, and will also fully release the OpenAMP bridging code as open source to ensure transparency, reproducibility, and ease of adoption. Take a look on the left. That is the Milk 5 Duo hardware. It's equipped with two RISC-V cores. The first one, often referred to as the big core, runs the Linux kernel. The second one, the little core, will be running ThreadX. Our goal here is to enable communication between Linux and ThreadX using remote proc, RPMSG, and ViRT-IO. Once everything is set up, we can check the Linux kernel log messages. There, we'll see the remote proc driver detecting and initializing the little core, and the ViRT-IO RPMSG bus showing the creation of the RPMSG channel, indicating that the messaging host is now online. The program begins by setting up an RPMSG endpoint, typically by opening a device file such as RPMSG0. This endpoint acts as a communication channel for bidirectional message exchange between the master and remote processors. On the Linux side, messages are sent using TX, and acknowledgements are handled with TX, ACK. On the ThreadX side, messages are received using RX, and acknowledgements are sent with RX, ACK. Ping-pong communication loop. On the master side, typically Linux running in user space, the system starts by sending a ping message through the RPMSG channel. It then waits for a response, either by blocking until a reply arrives, or by polling the channel periodically. Meanwhile, on the remote side, which might be a real-time operating system or a bare metal environment, the processor continuously monitors the RPMSG endpoint for incoming messages. When it detects a ping, it immediately responds with a corresponding pong message. This back-and-forth exchange continues for a predefined number of iterations. The goal is to verify that message passing and synchronization between the two cores are functioning reliably. Phase 1. Preparing and sending. Linux begins by placing data into a shared memory buffer located in the descriptor region. It then updates the associated metadata, including the buffer index and its length, and places this information into the available ring, which serves as a queue of buffers ready for processing. Once Linux updates the available ring, it sends an interprocessor interrupt to notify ThreadX that new data is ready. At this stage, the used ring remains unchanged and still contains entries for previously completed buffer transfers.
Phase 2. Consuming and reclaiming. Upon receiving the interrupt, ThreadX inspects the available ring and begins processing the indicated buffers, for example, those located at index positions 2 and 5. After ThreadX finishes reading and processing the data, it places the buffer descriptors into the used ring. This action marks the buffers as available for reuse. Later, Linux scans the used ring to reclaim these buffers and can then repurpose them for subsequent message transmissions.
I feel uncomfortable today, so I just prepare some pre-recording material. So right now we are going to implement the opposite sides communication between ThreadX and the Linux. So this is the inverse operation, and by means of RPMSG and the remote PLC. As I mentioned earlier, the source code is uploaded to GitHub, and you can follow the instruction if you want to build from source. So let's check this one. Once you get the source code, you will see some commit here. So initially, we add the ADB as the debug support, where you can use the ADB share or similar command in order to connect or transfer file between personal computer, your development board, and the RISC-V environment. In addition, we provide ThreadX as a submodule, so you can take it. And then we use the remote PLC driver. So here, let's go through the source code. In order to enable the remote PLC, we have to set several entries. So here, you can see we enable remote PLC in Linux kernel. Of course, we have to modify the device tree in order to provide the corresponding settings. So here you can see we reserve a region for remote PLC. Typically is reserved for SLN section, so that we can load we can set out the RISC-V by means of a configuration the little core running ThreadX or other RTOS. So this part is platform-specific settings. As the prompt message indicates, so we can enable remote processor framework as a loadable module. And then this is the main driver for remote processor. So we just modify the existing STM code base as a start. So everything looks quite straightforward. So everything we have to tweak in advance is specify the memory region and the underlying settings. Okay, so this is the enablement of remote processor driver. Then we prepare RPMSG driver. So we use the remote processor framework in order to load the firmware from Linux. And right now, RPMSG itself is in the communication mechanism. So right now, we just go through the source code we modify. Similarly, we have to enable the platform-specific remote processor settings. And right now, we have to enable RPMSG along with I/O, as I mentioned earlier. I/O is the underlying infrastructure for RPMSG purpose. Of course, we have to tweak the device tree. So here, we just set out the RPMSG by reserving the region. This part is used for the shared memory. So if you recall the introduction I mentioned earlier, so the shared memory itself is basic CR for RPMSG purpose. So we have to enable shared memory. Similarly, we have to prepare the shared memory driver, and we just modify the existing code base as well. So we modify the driver written by NSP as the starting point. So right now, it's quite similar. The first thing we have to modify is the mailbox. So here, you can check some description. This is a matter of the region setup. And here, we have to provide the callback for word queue since RPMSG relies on the word I/O. So we set out the callback. Once the ThreadX gets the information from the Linux, the callback will be invoked so that we can proceed the further action once required. Okay, so you can check the source code by your own. We just mentioned the part we modify. So before we use the RPMSG driver, we have to specify the endpoint. So here, EP1 is the endpoint we have to preserve in advance. So this is exactly the name. If you check the source code, we use this identifier in order to communicate between the user space and the kernel. This part is optional, but we still provide this header. So this header serves as the abstraction layer so that we can reuse the header not only for Linux, but also for ThreadX, FreeRTOS, and so on. So this is general command queue operations. Okay, right now we prepare the driver for RPMSG. So far, we have our own ThreadX build. So here, so we have the build for ThreadX, which is expected to run on the heterogeneous core, and we have prepared remote processor driver along with the RPMSG driver. So right now, we can move forward. There are many ways to set up the communication. You can use USB, RDS, or use ADB. And ADB is the way we recommend to use, since it's quite straightforward by means of the USB wire communication. Okay, good. So once you get the Milkify hardware, you can follow the instruction to build from scratch. Then you should be able to generate the system image, where Linux and ThreadX were built inside the image. And here, before using ADB, you should prepare the utility for Android tools. So here, you should install the package in advance. And then we can use ADB share. Okay, so we also provide several test programs, and you should be able to get the source code and test by your own. Here, you can see this one is a mailbox. So mailbox itself is used for the diagnosis tool to analyze the communication between Linux and ThreadX. Later, we will demo the usage of mailbox. In addition, we provide other useful tool for the demonstration purpose, so that you can utilize mailbox to set the state of ThreadX.
M programming comes with its own.
Okay, so
M programming.
So let's check the demo. Demo.
Okay, hi. I'm JK Chiu from Taiwan, by the way. Thanks everyone for coming here. And now I'm going to demonstrate how we use this program on a cheap device, on a very low-cost device called MicPhi. And MicPhi is smaller than a thumb, and it's very cheap. It only costs $9, but it's cheap and cheerful. Why? Because it contains a RISC-V big little core design and an AI compute coprocessor, and whole device can only run device run entirely off USB power. And you can see on the screen there's a LED light on the right upper corner. And we're gonna use that LED line to demonstrate how we use the interaction between little core and big core and little core to control that LED line. And like my friend Jing Huang mentioned before, we integrate ADB, Android Debug Bridge, to let us use Linux PCs directly into the big core on the MicPhi. By the way, there's two core on MicPhi. The bigger one is run on Linux, and the little one is run with ThreadX. And for the one who didn't familiar with ADB, there's two main commands we are going to use in this demo. One is ADB push. ADB push lets us to send a file from Linux PC to MicPhi. Another one is ADB shell. ADB shell provides you a shell interface from MicPhi, just like SSH. And all you need is a USB cable that powering the Mic5. And sorry. And like I said, we're gonna push a demo package from Linux PC to Mic 5. And after we open the ADB shell, we can see what in that demo package is. There's a script we call the remote processor script. What we do with this script, we download the ThreadX, which just copied from the Linux PC to the B core. We send that ThreadX image from B core to little core, and then we restart the little core, just like in that script. And after we compile that script file, we can see some interesting points from the log. The first one is that we successfully boot the image on the little core, and then the remote processor is now on. The creating channel RPMSG means that the channel are creating that's a key component to enable those core to communicate with each other. And then, and after that, we are going to use a program called Mailbox LED to demonstrate, like I said before, how to use the interaction between those two cores to control a LED line. Yeah, what this program is going to do, they will take a command from the bigger core to from the big core to little core. Okay, what we're going to do is that we are setting the blink period of the LED, and the right means how the program are running on the B core. That's the interface of ADB interface. So how the program are running on the B core, and the right means the B core send a command from B core to little core, and the read means the little core take the command from the B core. And as the video shows, the pause period of the LED line is set to 1 second, and now we are going to set it to 3 seconds. You can see that the pause periods are getting longer, and now we are going to set it back to 1 second. And of course, you can set to half second. Okay, so we just demo how we use the interaction between B core and little core to control the LED light. Now let's see how they interact internally. So we are going to sniff how the core interact during blinking. And we introduce another program called Mailbox Ping Pong. What's Mailbox Ping Pong? Mailbox Ping Pong is a program that can sniff the information that are exchanged between those two cores. Okay, so whenever an LED period command is issued, RPMSG always delivers the complete message sequence, as you can see. Thanks, everyone. Now I'm going to, okay.
So, so far, we just illustrate the usage for RPMSG and the remote processor framework. So, by means of OpenAMP, we can construct the heterogeneous computing environment, and through the package we provide, you should be able to construct everything you need with the powerful but still still inexpensive devices. So later, you might try to construct your own HAI application over some special scenario which relies on the strong isolation. So with such scenario, OpenAMP is really powerful. Okay, this is my email. Please contact me if you have questions. Any question?
So you said you use ADB to flash the main program to the big processor. How do you flash ThreadX updates to the little processor?
Okay, interesting question. So let's go back to the setup. So we can utilize ADB to prepare the transfer between PC and the RISC-V board. And the RTOS image, such as a ThreadX image, is preserved in Linux sites initially. And then we have to use a remote processor framework in order to download the image into the certain memory region. And then we have to reset. We have to issue the command to reset the processor. Usually, we call such core as a little core. So we can even automate the process, meaning that we can use ADB to push from the PC into the RISC-V boards running, the big core running Linux. And then we can use a remote processor to download from big core to little core in order to initiate ThreadX. And I answer you. Okay, thank you. Okay, thanks for coming. Thank you.